Hello friends, welcome to the Laplace transform. So myself is Dr. Shivlingappa Sangappa Bichadi, Professor at Department of Mathematics, Basaveshwara Engineering College, Bagalkot. Today we shall discuss about a Laplace transform. Why we want to study Laplace transform? Define a Laplace transform. Define a linearity property of a Laplace transform. These are the objectives of today's lecture. Friends, before defining a Laplace transform, I want to ask one question myself. Why I want to use a Laplace transform? Is it necessary or not? I can give the solution for this question or these questions, right? The important mathematical tool known as the Laplace transform is named the great French mathematician Pierre-Simon de Laplace between 1749 to 1827, who studied its properties, but it was probably used earlier by Euler's, right? So this transformation will be useful to us because it removes derivatives from differential equations and replaces them with algebraic expressions. In this way, differential equations are replaced by algebraic equations. The Laplace transform converts integral and differential equations into algebraic equations. It allows us to analyze complicated circuit with source, inductance, resistance and capacitance. Laplace transform is a powerful technique to solve differential equations. It transforms an initial value problem in ordinary differential equations to algebraic equations. The solution of the algebraic equations is then back transformed to the original problem or solving the differential equations of the circuit. Sometimes a function may be piecewise continuous or periodic. Could be difficult using the earlier techniques. Friends, it means that the given equation means most of the engineering problems can be written down in ordinary differential equation. Then we will find out the solution. How we are going to find the solution? First method is we will try to find out the solution by using an known method. Known method means we want to calculate complementary function plus particular integral. Then only we can expect a general solution. Is it clear? Here means suppose if I use a Laplace transform without calculating complementary and particular integral, directly we can obtain the solution. Directly means when we apply the Laplace transform, it can be converted into an algebraic equation. Once it becomes an algebraic equation, then immediately I can find out the solution. Is it clear? Right? So before defining, I wanted to use some more elementary information. Is it clear? So in elementary calculus, we learned that differentiation and integration are transforms. This means, roughly speaking, that these operations transform a function into another function. For example, the function f of x is equal to x square is transformed in turn into a linear function. A family of cubic polynomial functions and a constant by the operations of differentiation, indefinite integration and definite integration. It means that suppose if the given function is x square, then if I want to transform this function into a linear function, then what is the operator? I can use differentiation as the operator. By using differentiation, I can reduce it into a linear function. It means differentiation is also an transformation method. Or we can ask a question like this: how do we convert parabolic curve into a straight line passing through the origin? Straight line passing through a point 0, 2, non-parabolic curve passing through the origin. Is it clear? It is very simple to answer these questions, right? So they have given a curve. Is it clear? Y is equal to x square. Then you can transform by differentiating. I hope you'll get a 2x. You'll get a curve x. Is it clear? Right? So then if you differentiate one more time, I hope you'll get 2, and if you integrate, you'll get 1 by 3 times of x cube. You'll get a curve like this. It is also called as transformation. Is it clear? And we are already familiar with the linearity property in differentiation and integration. Suppose if I apply differentiation on alpha into f of x plus beta into g of x, where alpha is a constant, beta is a constant. Keep constants as it is. Apply derivative on the function. I hope we can obtain f single prime of x, g single prime of x along with the arbitrary constants. Exactly in the similar way, if you apply an integration symbol on the same function, you can keep constants as it is. Integration of f of x plus constant into integration of g of x with respect to x. Is it clear? These properties we may call it as an linearity property in differentiation and integration. We can extend the same property to for definite integral also. Is it clear? Okay, now we have acquired some basic knowledge to define a Laplace transform. Friends, now we are capable to define the Laplace transform. Let f be a function. Sometimes we may call it as an signal defined for t is greater than or equal to 0. Then the integral 0 to infinity e raised to minus st f of t dt is equal to f of s. Is it clear? Here L is the operator you can apply on f of t. So what you will get? Right hand side form, or we can say that a function of s. Is it clear? For those s belongs to c, it means here s belongs to c. C means what? Set of all complex number for which the integral makes sense is said to be Laplace transform of f, provided the integral converges. The result is a function of s. After integration, what you will get? Finally, you will get a s. Right? So f is a complex valued function of complex numbers. Small s is called the frequency variable with unit set to the power minus 1. T is called the time variable in second. S into t is unit less. So like that you can define the Laplace transform for the given function. Is it clear? Few more forms are there, so I can give all the forms, right? So before that I wanted to concentrate on the notations. Is it clear? Right? So because we can use different notations in a Laplace transform. If a function t is indicated in terms of lowercase letter such as f of t, g of t, y of t, etc. Right? The Laplace transform of these functions, how we are going to denote capital F of s or g of s, y of s. Is it clear? Or in other words, we can use the Laplace transform of u of t is denoted by u tilde. This is symbol we call it as an u tilde. If you transform u of t, you will get u tilde of s. So like that we can use the different notations. Right? So we can use the same definition in other form. Right? Friends, here we are going to transform two variables. Right? Namely t and s. Is it clear? So I am going to transform t to s. Right? How we are going to transform t to s? Using the integral symbol. Is it clear? Right? So integration of 0 to infinity e raised to minus st f of t dt is equal to f of s. Is it clear? Here s is the parameter. It may be real or it may be complex. Is it clear? Before calculating, I want to verify the given function is eligible for the Laplace transform or not. Is it clear? Right? So how do you verify? I have to verify the condition. What is that condition? Function must be piecewise continuous. F of t is a function exponential order. Any function satisfy this condition, then I can say that it is eligible for the Laplace transform. Then only I can find out Laplace transform of that function. Is it clear? Then you may ask, what do you mean by piecewise continuous? You can divide the interval 0 to 3 into sub-intervals, and if you consider any sub-interval, in that case function is continuous. That's why we can say that piecewise continuous. You can take any piece, it is continuous. That is the meaning. Or I can give few more mathematical details of the piecewise continuous function. interval a to b. If the interval a to b can be broken into a finite number of subintervals, you can divide the interval in this format such that f is continuous in each subinterval, say ti plus 1, I is equal to 0, 1, 2, 3 and so on. The function f has a jump discontinuity at ti. It means it satisfies these conditions. Is it clear? Right? For example, the function is defined by f of t is equal to t square, where t lies between 0 and 1 is equal to 3 minus t. It lies between 1 and 2. T plus 1 to t lies between 2 and 3 is called a piecewise continuous in the interval 0 to 3. Consider any piece function is continuous. That's why we call it as it is a piecewise continuous. Is it clear? Or you can give another example. F of t is equal to 1 over 2 minus t. T lies between 0 and 2 is equal to t plus 1, where t lies between 2 and 3 is not a piecewise continuous. Is it clear? You can observe the graph. We'll come to know that it is not an piecewise continuous function. Is it clear? Exactly in the similar way, we can verify the exponential order, whether the function is exponential order or not, because it is an important. A function f is said to be exponential order c. C is some constant. If there exists a constant c, m is greater than 0 and t is greater than 0, such that mod of f of t is less than or equal to m into e to the power c into t for all t is greater than capital T. If t is an increasing function, then the condition mod of f of t is less than or equal to m into e to the power c into t. T is greater than t simply states that the graph of f on the interval t to infinity does not low or does not grow faster than the graph of the exponential function m into e to the power c into t, where c is a positive constant. For example, you can take f of t is equal to t, or f of t is equal to e to the power minus t, or you can take f of t is equal to 2 times of cos t, or all exponential order c is equal to 1 for t is greater than 0, since we have respectively mod of t is less than or equal to e raised to t, mod of e to the power minus t is less than or equal to e to the power t, mod of 2 times of cos t is less than or equal to 2 into e to the power t. It means all the three functions satisfies the condition. That's why I can say that exponential order, or these are the examples of exponential order. You can compare these graphs. So this graph will not allow to grow independently. That's why I can say that these examples are the examples of exponential order. Is it clear? Right? So still I am not happy with the definition of a Laplace transform. I can define the same definition on the other words. Is it clear? So mathematically, so you can write down as usual integration of 0 to infinity e raised to minus st f of t dt is equal to f of s. Is it clear? Right? In terms of words, I can define the same function in this form. Given f, a function of time with value f of t at time t, the Laplace transform of f is denoted by f of s, and it gives an average value of f taken over all positive values of t, such that the value of f of s represents an average value of f taken over all possible time intervals of length s. So like that we can define. Thank you very much for watching this